Presentation of Science Trek on Idaho Public Television is made possible through the generous support of the Laura Moore Cunningham Foundation, committed to fulfilling the Moore and Bettis family legacy of building the great state of Idaho. By the Idaho National Laboratory, mentoring talent and finding solutions for energy and security challenges. By the Friends of Idaho Public Television, and by the Corporation for Public Broadcasting.
Chemistry is the branch of science that deals with matter, the elements that make up everything in the universe and how they interact. We're going to answer some questions and do some experiments. Stay tuned. Science Trek is next. Hi, I'm Joan Cartan-Hansen, and welcome to Science Trek, and welcome to a lab at Boise State University's Chemistry Department. Today, scientists are standing by to answer your questions about chemistry, and later on we'll learn a little bit more about matter. But first, let's find out about chemistry.
An atom is made up of three parts: neutrons, protons, and electrons. The protons and neutrons combine together to make the nucleus, and the electrons circle around the nucleus, making up an atom. An element is a substance that contains only one kind of atom. Scientists have discovered at least 118 different elements in the universe so far, but only 94 of them are found naturally on Earth. Things like helium and carbon. Elements are grouped together in a chart called the periodic table. Each element fits into its own square. Each element has its own chemical symbol, its own atomic number, that is, how many protons are in that element's nucleus, and its own atomic mass, which is how many protons and neutrons fit in the element's nucleus.
An element is a substance that contains just one kind of atom. Gold only contains gold atoms, but if you combine two kinds of atoms, like hydrogen and oxygen, you get water. That's known as a compound.
Chemists study how elements react when they combine. Some reactions are spontaneous, like rust on iron. Other elements need heat or pressure to react. All chemical reactions either absorb or release energy.
If you want to see a chemical reaction in your mouth, try biting down on a wintergreen lifesaver while looking in the mirror. Oh, I forgot to tell you, you have to do it in the dark.
One of the important things about chemical reactions is that they're predictable. Scientists can count on the same thing happening every time the elements are combined. Cooking is a chemical reaction. Ingredients combine together and you heat them up. And because chemical reactions are predictable, you know your cookies will turn out the same way each time you make the recipe.
Yum!
Scientists use chemical reactions to make things, like the plastics in your toys, or the rubber in your bike's tires. And chemical reactions keep us alive. Breathing, or respiration, is a chemical reaction. And so is digestion. Chemicals help us do things, make things. It starts with atoms that make up elements. Elements combine to make compounds, and combining elements or compounds results in chemical reactions. So chemistry is part of just about everything we do.
And joining me now to answer your questions about chemistry are Kathryn Devine, Associate Professor of Physics at the College of Idaho, and Christopher Saunders, a lecturer in the Department of Chemistry at Boise State University. Thank you both for joining us.
Thank you for having us.
Thanks, Joan. It's great to be here.
Okay, let's go to your questions.
Hi, my name is Tyler, and my question is, what exactly is chemistry?
Hi, Tyler. Great question. So the simple answer is that chemistry is a study of matter, and matter is the stuff that makes up everything that you see and feel around you. So in some ways, you can say chemistry is a study of everything and how all of that stuff that makes up the universe interacts with each other.
Hi, my name is Haley. My question is, what are atoms?
Atoms are the fundamental building blocks of matter. And so if you take matter and look at the tiniest things that make it up, you'll find atoms. For example, hydrogen is an atom, oxygen is an atom. And if you take 2 hydrogen atoms and an oxygen atom and put them together, you'll wind up with a molecule of water. And so everything around us is made up of molecules and atoms and these tiny particles that that build up our world.
Hi, my name is Amelia, and my question is, how did scientists decide which elements are on the periodic table and what order they're in? Also, if you could be one element, what element would you be?
So the periodic table, some would argue, is one of the most important aspects of chemistry. And the person that is credited with the construction of the periodic table, even though many people contributed to it, was Dmitri Mendeleev. And Dmitri Mendeleev imagined a way to organize the elements based on the number of protons that you find in the nucleus. So each individual element is on the periodic table in order of how many protons are in the nucleus. So all of the elements that we know have a place on the periodic table. And even now, we are discovering and we are able to make new elements. Just this last year, 4 new elements were officially added to the periodic table. The order and the way that the periodic table is organized also tells us something about the chemical properties of those elements. So Mendeleev had a really unique understanding of the different types of properties and the way that he ordered those elements on the periodic table far before he knew, or science knew, that all of these different elements existed. I think that my background is biochemistry. And so I think that carbon, which all life that we know of is based off of, I think that would be the atom that I would be. Carbon is central to organic chemistry and to biochemistry, and without it, none of us would be alive.
I think I would have to be hydrogen, because hydrogen, I'm an astronomer, and hydrogen is the most abundant element in the entire universe. And so there's more hydrogen than anything else. And studying hydrogen and its emission lines is one of the ways that astronomers have figured out a lot of things about the size of our own galaxy, the distribution of gas in our own universe. And so I would definitely go with hydrogen.
Hi, my name is Kyle. I was wondering what chemicals are in dry ice.
Well, that's a really good question. So instead of just explaining the answer to the question, I figured that you might like to see dry ice itself. So here's a piece of dry ice. So notice that I'm wearing gloves. Dry ice is very cold. This is about at 110 degrees below 0, so super cold. So right now, even though you might not be able to see it, this dry ice is turning into a gas. And you might go, well, what gas is it turning into? Well, dry ice is a solid form of carbon dioxide. The same carbon dioxide that you're breathing in and breathing out right now, the same carbon dioxide that plants use when they breathe in the gas that they use to make their food. So you might be saying, well, how do we know that this is made out of carbon dioxide gas? One of the ways that we know that this is made out of carbon dioxide is that we can test some of its chemical and physical properties. And one of those is that carbon dioxide can be used to put out flames. Certain fire extinguishers use carbon dioxide to do that. It pushes out all the oxygen that the fire needs. So what we have here is a beaker, and that beaker has tiny pieces of the dry ice in there, and it's been filling up with carbon dioxide gas as I've been talking. So what Katie's going to do is she's going to try to put a flame inside the carbon dioxide, and I want you to watch what happens when she tries to do that.
Okay, so I've got a flame here, and it's burning just fine in the air of the room.
So you notice when she puts the candle into the beaker, it instantly goes out. Now you might be saying, well, that's just because she dropped it, and dropping it put it out. So now she's going to take that lighter and try to light it inside the beaker. And notice that she can't do it. Every time the flame gets below the top of the beaker, it's now in the carbon dioxide gas, there's no oxygen gas, and the flame can't stay lit. So let's do another experiment with the dry ice. So remember that we have this solid form of carbon dioxide, and that carbon dioxide is turning into a gas through a process called sublimation. So it might not be very exciting just to stare at a piece of cold carbon dioxide. So let's speed up that process. To speed up the process, we're going to take the dry ice and we're going to put it into some warm water and watch what happens. So what you notice now is you've got this really cool looking fog. And actually, this fog is made out of the same things that you see that clouds are made out of. So what you're seeing is not the carbon dioxide, but you're seeing the water vapor in the air. And so that water vapor is condensing because the carbon dioxide gas is really cold. So really what you're seeing is a form of clouds being produced in the container.
Only 2 elements are liquid at room temperature, bromine and mercury. Only 2 metal elements are not silver in color, that is gold and copper. And only 1 letter doesn't appear in the periodic table, and that's the letter J.
Hi, my name is Ashley, and my question is, why are some chemicals poisonous to people, and why aren't some chemicals poisonous to people?
So that's a really complicated question. And one of the ways that I would answer that is that even things that you may not think of as being poisonous or toxic to people can actually be toxic in the right dosages. So a lot of talking about what is harmful to someone is dependent on, well, how much of that stuff you are exposed to. For example, water, right? You drink it, you take a bath in it, it's required for life. If you were to drink too much water, you could get really sick. If you were to drink even more water, you could even die. So even though we don't think of water as being toxic, it can be toxic in large amounts.
Hi, my name is Emerson, and my question is, how is baking chemistry?
So just like in chemistry, baking, you can rely on different chemical reactions to get different results. And so one of the most common examples is the use of baking soda or baking powder. And there's some slight differences between the two of them, but both of them rely on acid-base chemistry. So let's take baking soda, for example. So you put baking soda in a cake mix. Okay? When you heat that up, that baking soda is going to dissolve in some water, and it's going to interact with an acid. And that acid-base reaction is going to produce carbon dioxide gas. And this is what makes the cake or rolls or bread fluff up. It's that carbon dioxide gas that's being produced in the reaction to fluff up those things that you like to eat.
Hi, my name is Cora. My question is, how does liquid nitrogen and dry ice stay so cold?
So if you have anything that's very cold or in fact very hot, and you put it out in the open, it will reach what physicists and chemists call thermodynamic equilibrium, meaning it'll eventually become the same temperature as the room around it. And so to prevent that from happening, you take your liquid nitrogen or your dry ice, and you have to put it in something that's insulated to keep it from reaching equilibrium with its surroundings. And so you insulate it just like when you wear a coat when you go outside to insulate yourself from the cold. If you insulate your dry ice or your liquid nitrogen, that will keep it from reaching the same temperature as the surroundings.
Hi, my name is Maya, and my question is, can you mix 2 chemicals without it making a chemical reaction?
It's a great question. So let's do some experiments to explore that. So here I have a couple of test tubes, and in each test tube you'll see a clear colorless liquid. Now you have to trust me on this, but both of these liquids are not the same thing. So one of them is water, and one of them is rubbing alcohol. So I'm going to mix them together, and let's watch what happens. So you'll notice that maybe at first it got a little cloudy, but now there's not really much happening. And so while the two things have mixed together, there's no chemical reaction taking place, at least none that is visible. So sometimes chemical reactions can be very visible. And so let's have Katie do an experiment where you'll see something similar but a much different result.
So I'm going to take potassium iodide and put it in the first test tube.
So you'll notice that Katie is mixing 2 chemicals, and both of them are clear colorless liquids, just like the ones that I had. But she's going to get a much different reaction when she mixes those 2 things together.
So the second chemical that I'm going to load into a test tube is lead nitrate. And now I'm going to take the lead nitrate and the potassium iodide and mix them together and see if we get a reaction similar to what happened with Chris, where nothing really visible happened, or if something different happens.
So you can see that the moment that the liquids mixed, that there was a reaction happening. We get this brilliant yellow color. The yellow color that you're seeing is the formation of lead iodide. So there was a chemical reaction in which the two liquids mixed together and created something new. And that yellow product is what you're seeing.
Matter is a physical substance that takes up space and has mass. Matter and chemistry go hand in hand, so let's learn a little bit more about matter.
Anything that takes up space and has weight is called matter.
When we say anything, we really mean it.
Your favorite food is matter. Your bike is matter. Even your school is loaded with matter.
Matter can be as small as the tiniest cell in your skin, or as large as the whole galaxy. Matter is made of atoms. Matter has mass or weight. Matter can also change from one form to another. The study of matter and the changes it goes through is called physics. Matter comes in 4 basic states or phases: a solid, a liquid, a gas, or plasma. There are other forms of matter, for example, one called Bose-Einstein condensates. But these exotic forms of matter exist only in laboratories and aren't found naturally on Earth. So let's first talk about solids.
Solids happen when the atoms of matter are densely packed.
Just look around your house. Can you spot a solid? Something that won't change its shape when you touch it. Your bike or a computer are both good examples of a solid.
How about the next state, liquid? Water, milk, and juice are all good examples.
In a liquid, the atoms aren't as closely packed, and the matter takes on the shape of what's around it, like water in a glass. Next, there are gases. The atoms in gases are spread out and bouncy.
Gases are usually invisible and have no shape. Unlike a liquid, you cannot spill it, and unlike a solid, you cannot touch it.
A gas, like air, is easiest to see when we fill up a balloon or watch the wind blow. And then there's plasma.
It can be kind of tricky to spot if there's a fluorescent light in your house. If there is, then you found plasma. The light it makes is glowing plasma.
You also see plasma when you look at the stars. Stars are big balls of gases at really high temperatures, and high temperatures charge up the atoms and create plasma. Temperature is one of those physical forces that can change matter from one form or phase to another. By changing the temperature, either hot or cold, you have added or subtracted energy. You've made a physical change in the matter. But even if the matter takes a different form, its chemical makeup doesn't change.
Take water, for instance. It's made of 2 hydrogen, 1 oxygen, and if you heat it, it turns to steam. If you freeze it, it turns to ice. But what doesn't change is what it's made of. It's still water.
The physical state of matter, whether it's a solid, a liquid, a gas, or plasma, is a description of the state of its atoms. Matter is large and matter is small. It has mass or weight, and it can change its form.
It's basically all the stuff around you, no matter its state. Hi, my name is Amaya, and I was wondering what 2 liquids have the biggest chemical reaction when mixed together.
So in terms of thinking about a big chemical reaction, I would argue that one way to think about that is that in terms of how much energy comes out of the reaction, or you think about an explosion, or you think about fire, or something like that. So while they may not be liquids, the kind of reaction that I can think of that has the biggest release of energy is actually a nuclear reaction. So in this case, fusion. So taking the nuclei of 2 different isotopes and fusing them together, basically taking protons and neutrons and shoving them into the same space. When we do that, a lot of energy is produced.
And that energy produced is actually, you've probably heard of Einstein's equation, E equals mc squared. And so what that equation is saying is energy equals mass squared. And so an equation that describes that mass can be converted into pure energy. And so that lays the foundation there. And this idea of fusion and E equals mc squared is actually the source of the energy that powers our sun and all the other stars.
Hi, my name is Brody. My question is, what is the chemical mixture that makes the surface of Mars poisonous?
So the surface of Mars isn't actually poisonous, and so a lot of the things on Mars, the surface of Mars, the rocks on Mars, are very comparable to the geology and the rocks that we have here on Earth. The reason that you couldn't walk around on Mars without a spacesuit and an oxygen tank on are because the lack of atmosphere. And so when you're here on Earth, sitting in your room and breathing, you're breathing air, and air is a mixture of nitrogen and oxygen and argon and a couple other elements. And that atmosphere is all around us, and there's quite a lot of it, and we need it to survive. And if you went to a planet like Mars that didn't have that atmosphere, you wouldn't have air to breathe, and that's what would kill you rather than anything toxic on Mars.
And even though Mars doesn't have much of an atmosphere, the little bit of atmosphere that it does have is over 90% carbon dioxide. The same carbon dioxide that you breathe in, but at much higher levels. And again, like Katie said, there's just not enough oxygen in that atmosphere for you to be able to breathe it safely.
Hi, my name is Scott, and I go to Dalton Elementary. And my question is, why are Newton's 3 laws so important?
So Newton's 3 laws describe forces in motion, and they were really important because at the time they started to describe physics in terms of rules, and it really laid the groundwork for what we teach now as modern physics. And so Newton's laws, that an object in motion will stay in motion unless acted on by an outside force, and so that's describing something, a push or a pull, the forces. That force is related to the object's mass and acceleration, so the more force you apply to something, the more you can change its rate of speed. And then the third law, that every force has an equal and opposite force. And so those describe forces and how they impact motion and really set up our modern study of physics.
Why did you want to study chemistry or physics?
So for me, I've been interested in science since elementary school. I had a really great science teacher in elementary school, and she really made me excited to discover what makes up the universe and how do all those things work. So I've been interested in chemistry for a very long time.
And like Chris, I also really enjoyed science starting at a young age. And so in elementary school it was my favorite subject. And then in high school I studied all the science classes that I could. But I didn't really know what type of chemistry or physics or science that I wanted to do. I started out thinking maybe I wanted to do biology, and then it was geology. And I wound up in a physics class and realized that physics really helped explain a lot of the processes that you see in other sciences. And so that was why I decided to stick with physics.
Hydrogen is the most abundant element in the universe, but there are 10 million known compounds, that is, something that can be made of more than one element, which can be made with carbon. For example, a single human hair is made up of about 1 million carbon atoms.
Hi, my name is Cole, and my question is, how do you make a baking soda volcano?
Well, I've got to admit, I've made more than one baking soda volcano in my time. So what I've got here is an Erlenmeyer flask that's kind of substituted as our volcano. Notice it's kind of volcano-shaped. So imagine that this is the lava down here. It's going to push up, and when it's going to reach this neck, in theory, it's going to come shooting out of the top. So inside the Erlenmeyer flask is our baking soda. Okay, so another word for that is sodium bicarbonate, and we're going to mix it together with an acid. And so this is an example of an acid-base reaction. And so Katie, since you asked about a volcano, we figured we would add appropriate food coloring to the mix.
So let's make it look more volcano-like. We'll give it some volcano colors here, and these don't serve any purpose aside to make it more decorative. Chris, you've done this before. Do you think that's going to be enough lava color?
I think it should be enough.
Okay. Got some yellow and red colors to make it look more like lava.
So I've got some acetic acid here. You might know it more as vinegar. So I'm going to mix the vinegar with the baking soda. We're going to have an acid-base reaction. One of the products of that is carbon dioxide, and that's what's going to make it bubble and, in theory, come out of the top of this. While I do this, I'm going to take a step back. And there you have your baking soda volcano.
Hi, my name is Caleb, and my question is, how do light bulbs work, and how are light bulbs now more energy efficient?
So there's the old-fashioned light bulbs, which have a filament inside. And the way those work is you have that filament is basically a wire, and when you screw it into a light bulb or a socket, current runs through the filament and heats up the filament. And so as the current runs through, the wire heats up, and it heats up enough that it starts to emit light. And so the light is given off in the forms of the visible light we see with our eyes, but also in terms of infrared light, which we can feel as heat. So if you were to put your hand near one of those old-fashioned light bulbs, you would feel heat coming off of it. Newer light bulbs, or the CFL or compact fluorescent light bulbs, have a gas inside of them. And so when you screw in one of the CFLs into your socket, the current actually excites the electrons up to higher energy levels in the gas inside of the light bulb. And as those electrons cascade back down, they give off photons, which then hit the coating on the inside of the light bulb, which causes a phosphorescence, or a fluorescent reaction. And that gives off the light we can see with our eyes. And the reason those are more efficient is because if you put your hand near a CFL light bulb, you won't feel as much heat as you would from a filament light bulb. And so they're giving off energy, but more of the light, or more of the energy, is given off in the form of light that we can see with our eye in a CFL light bulb. So they don't have the loss of energy in terms of heat, and that makes them more efficient.
If someone is interested in becoming a physicist or a chemist, what should he or she study in school?
You kind of have to study everything. Math is really important to the sciences, and I think that doesn't necessarily get talked about enough. And so to do science, you really need to be able to do a lot of math. And so doing well at math is crucial. But also scientists have to be able to communicate their results to everybody. And so you have to learn how to write well and communicate well. And also now more and more importantly, knowing how to program a computer is very important to science. And so understanding computer science is an important topic for scientists.
So I would suggest that anyone interested in the sciences, obviously take a lot of science classes, see what interests you, but also don't forget about the non-science classes. Don't forget about your math classes. Don't forget about your English classes. Communication as a scientist is really, really important. You know, who cares about your fantastic results unless you can actually talk about those fantastic results with people who aren't necessarily scientists? So take as many classes as you can. Find out what you're interested in, and just because it's not science doesn't mean it won't be useful to you as a future scientist.
I'm sorry we've run out of time. My thanks to Kate and Chris for answering students' questions today.
Thank you so much for having us. This was fun.
Thanks. You all had great questions.
My thanks also to the folks at Boise State University's Chemistry Department for hosting us. You can learn more about chemistry and lots of other scientific topics on the Science Trek website. We'll answer more questions about chemistry on Science Trek, the web show. And if you want to submit a question for Science Trek, it's easy. You can send it as an email or a video question, recorded on your webcam or cell phone. And if you're an educator, we'll even lend you a camera. And each week, check out my blog for the latest science news for kids. You'll find all the details at idahoptv.org/Science Trek. Thanks for joining us. We'll see you next time on Science Trek.
Presentation of Science Trek on Idaho Public Television is made possible through the generous support of the Laura Moore Cunningham Foundation, committed to fulfilling the Moore and Bettis family legacy of building the great state of Idaho. By the Idaho National Laboratory, mentoring talent and finding solutions for energy and security challenges. By the Friends of Idaho Public Television, and by the Corporation for Public Broadcasting.
If you want to learn more about this topic or watch our videos, check out the Science Trek website at idahoptv.org/Science Trek.